Congratulations, you're moving on to R3. So that's looking specifically at vertex form of equations. Up until now, we've strictly looked at the general form, which is y equals ax squared plus bx plus c. So now we're going to switch it up a little bit. Before we get into what exactly is vertex form, I want you to do the following activity. If you're already comfortable using Desmos, please pause the video now and switch over to Desmos and get to work. If you are not comfortable using Desmos, I'm going to quickly run you through part 1 of this activity so that you can get a little bit more comfortable with it. So part 1 asks us to graph the following equations. So we're given 4 different functions: x squared, 2x squared, 3x squared, and 4x squared. So I'm going to switch over to Desmos, and we're going to enter that in. So y equals, and just x squared is my first equation. Now if I go down and click below it, I can create a space for a second one. Y equals 2x squared, and y equals 3x squared. Finally, y equals 4x squared. And so we get our graphs showing up on the same page, and we can see our functions. What's nice about Desmos is that instead of a graphing calculator is that it actually color codes these lines. So I can match and say that my widest parabola is matching with my parent function, that just plain old x squared. Then my next widest one is the 2x squared, 3x squared is the next, then 4x squared is the narrowest of them. Now you'll notice that it just shows 1 point. That is the vertex of all 4 of these functions. If I zoom in, keep zooming in, and I keep zooming in, no matter how close I go, we see that those parabolas are still intersecting all at the vertex 0, 0. They're all opening upward, and as we increase this number here, we see a change in the graph. Now what's really cool about Desmos is that we can actually create a slider, is what it's called. A is a slider. Now I can slide up, and I can kind of go all the way up to 10 is my coefficient here, and I can go back down to 0. So you can play around with that for a little bit if you want, but that's kind of funky. If I stay in the positives and above 1, that's what happens to my graph. Okay, dealing with the slider, that can also help you skip some steps in terms of plugging in specific functions for later parts of this activity. But for now, we'll go back to Notebook and answer the questions that go with this graph. How do their appearances vary? So these 4 different functions, how do they vary in terms of the width of them and the direction of opening? So we could say that they all open upward, but they do get narrower and narrower with an increase in their coefficient. So that would be part 1. Those are some observations. If you noticed anything else, you can write that down as well, and then move on to part 2. You're going to continue doing this for parts 1, 2, 3, 4, and 5. Once you have done those parts, you are going to complete a conclusion. Do all the graphs look the same? Yes or no. You might kind of argue both, feel torn about that question. That's okay. And then part B, write the rules to describe the trends you notice in each part of the activity. So part 1, part 2, part 3, part 4, and part 5. Can you write some rules to tell us about what we can always expect given specific changes? But I'll let you do that on your own. You can pause the video, and I'll wait for you. Moving on. You should have done the activity. If you didn't do the activity, do it right now. Right now. Go back to the previous page and go do it. Use Desmos on your phone, use Desmos on your computer. I don't care where you use Desmos, but you need to go and do it. You could even technically do it by hand. It's just going to take you a little longer. So quadratic functions in vertex form. This baby here kind of functions the same way that y equals ax squared plus bx plus c worked for a general form. So this is what we call vertex form. A represents the width of the graph, and so it can either stretch or compress it, and it also impacts the direction it opens, either up or down. So if the absolute value of a, so just the number a, ignoring whether it's positive or negative, the absolute value of a is bigger than 1, then the graph will be stretched. It'll be narrower. So you can think of that like a piece of gum or silly putty or anything like that, where when you pull on it and make it longer, the middle of it actually gets skinnier and thinner. So the same effect happens on our parabola. If our absolute value of a, so again just the value, not looking at whether it's positive or negative, is between 0 and 1, the graph will be compressed. So again, thinking about that gum that you're not supposed to play with, you go ahead and squish it between your fingers, it kind of oozes out the sides because it's getting wider. That matter needs to go somewhere, so it goes outwards. Same thing happens with compressing it. It's like we're pressing it down along the y-axis, pressing down from the top, and so it results in a wider graph. If a multiplying value out in front is negative, then the graph will open downward. Part P, this guy right here, it represents the horizontal shift of the graph. If that number is positive, the graph will shift. If you're not sure, go back and look at your activity. Maybe what did you notice? It will actually shift it right. If P is negative, the graph will shift left towards the negative values of x. Now the problem with this is that when we look at our general equation for vertex form, we've got a negative out in front of that P. We're subtracting it. So when we plug in a negative, say P is -2, when we go to plug it in, we get y equals ax minus -2 squared plus q. Well, a negative and a negative kind of work against each other, and it's like adding a positive. So all of a sudden it looks like y equals a times x plus 2 squared. This is where it gets a little bit confusing. We've got opposite signs affecting our x value. Finally, we've got q. Q's tacked onto the end at the back. So this is a number that if we had just kind of glanced at it, we might think that it's our constant term. We might think that it's our y-intercept. But because we've got that possible number in for p, unfortunately, it doesn't always work that way. So do not assume that q is your y-intercept. Instead, q represents the vertical shift of the graph. If q is positive, the graph will shift upward. And if q is negative, the graph will shift downward. This, fortunately, is a little bit more intuitive than that p value because it's being added to my equation. So the sign of q in the equation is going to directly correspond with the actual value of q, including whether it is positive or negative. So we've got all this information. We also know that p and q together describes the position of the vertex. This is why it is called vertex form. We've got example 1, which is asking us to graph each of the following equations and identify the properties of their graphs. We're going to graph y equals x squared. So we already know a few things about this graph. It is negative infinity to positive infinity for the domain. It goes from 0 to positive infinity for the range. Its axis of symmetry is x equals 0 because the vertex is at 0 and 0, meaning that it's opening upwards based on our range. And here's our vertex, so our minimum is at y equals 0. X-intercepts 0. Y-intercepts, it's at 0 as well. Plot my points, make sure I put my scale in. Now again, if you are not confident in your kind of data that you plug in, you can always graph your function first and then build from there. But we've seen this particular parent function. Okay, and get used to hearing that. That's like the very stripped down to the bones basic equation. Okay, we've seen it a few times, so I already knew how to graph that one. Okay, we also want to make sure that we have our graph labeled. We've got our x and y axis, and we want to draw in our axis of symmetry. Okay, so that's our parent function. Let's see what else we have to do. Apply these rules, that's what we have to do. So the second we see x squared, or a square in an equation, and that's our highest degree, we know we're talking about a quadratic equation. Here, I don't just have an x squared, but I also have another term, which is plus 1. This particular plus 1 is in the position of q, which means I'm going to have my parent function moved up 1. Because that's what q does. It moves things up just by 1. So again, I'm going to put in all my scale. I'm going to label my axes. And then I'm going to start plotting some points. So I've shifted it up 1. So all of these points, it used to be at 1 and 1. Now it's going to be at 1 and 2. This point was at 2 and 4. So that's 2 squared is 4. Then plus 1 is now 5. Same thing on this side. Negative 1 squared is 1. Plus 1 is 2. Negative 2 squared is 4. Plus 1 is 5. So I keep my symmetry even though I've shifted my graph. It keeps its shape. So that's why it's important to recognize that all quadratics have this parabola shape, because its shape is going to stay relatively constant. We can stretch it, we can compress it, we can move it around, but in the end it will still be a parabola as long as x squared is your highest degree. From here, I can state my domain, negative infinity to positive infinity. In this case, my bottom of my range is going to be 1, and the top of my range is still going to be infinity. Those arrows are pointing upward forever. My axis of symmetry this time is still going to be x equals 0 because I haven't horizontally shifted it at all. My vertex is now at 0, and not 0, but positive 1. So my minimum is at y equals positive 1. X-intercepts, now I no longer have any intercepts for my x-axis, so I write none. Do not write 0. That is wrong because 0 is a possible value for your x-intercept, as we saw in the previous question. So don't write 0, write none, or no real roots is a better way of wording it. Okay, our y-intercept, we do still have one of those. It is going to be 1. Looking at C, it follows the same exact pattern as B. So we're still looking at our q value. It's still following the squared term. It's outside of being squared, so it's part of q. So that means that instead of moving it up, I'm going to shift my graph down 2. So sorry about the fan noise. I'm using this loaner surface. It doesn't have as big a memory as mine does. So we've got negative 2 as my q value. That means that it's shifting my graph down 2. I could also have figured that out by plugging in, making a table of values. You're totally welcome to do that. These videos are long enough without me doing that, so I'm going to keep going. Negative 1 squared, if I plugged it in, is 1. Minus 2 is negative 1. And again, I've got that symmetry going on. 2 squared is 4. Subtract 2 is just positive 2 now. And then 3 squared is 9. Subtract 2 is 7. And that actually fits nicely onto my graph here. So now I actually fit a couple more points on to get my shape correct. Remember, No V's down here. Smooth it out. Okay, so my domain, like usual, negative infinity to positive infinity. If we're wanting to write our set notation, it would be x as an element of the reals. My range is going to be, in this case, still a minimum, still opening upward, but now it is at -2, that bottom, to positive infinity. Or if we're doing set notation, y is an element of the real numbers, but y has to be bigger than or equal to -2. My axis of symmetry is still through my vertex, and I haven't moved horizontally, which means it is still x equals 0. The vertex itself is at 0 and -2 now. So a lot of people at this point get super confused because we've got brackets going on with the interval notation, but then we've also got these brackets for our vertex. Their meaning is different, so you need to be really conscious to label what you're talking about, because if I see just rounded brackets at 0 and -2, that means I've got a graph that exists only between 0 and -2. You've written it in the wrong order because minimum always goes first, and that's very, very confining, and these parabolas have very big domain and range, so we've done something wrong. So make sure you label all your information. Maximum and minimum still opening up, so it's minimum at y equals -2. X-intercepts, now I have 2 of them. I'm going to have to solve for them. So in this case, I'm going to plug in 0 for y equals x squared minus 2. That means that 2 is x squared. Take the square root of both of those. That leaves you with x equals plus or minus the square root of 2. Now again, I should have 2 answers here because we see it on our graph. We've got 2 different x-intercepts. Also because if I introduce the square root into an equation, I don't know whether that number that was being squared was positive or negative. I just don't know. I can't assume one or the other, so I have to assume it could be either possibility. So my x-intercepts are at positive and negative the root of 2. Just going to fix that sign so it's a little cleaner. My y-intercept's a little bit more obvious. It's at -2, and we're done. Moving on. Does this look the same as b and c? I hope you said no, because that constant that we're adding, that other term, is actually inside the brackets. It is part of our square, which means that as inside our function, it is affecting our x value. It is a p-value. P. And remember, p has the sign switched because it should be negative and then -1. And so p is -1. This means that my graph is shifting left by 1. It hasn't shifted up because there's no q value. It hasn't shifted down because there's no q value. So I'm going to go about my business and just move the vertex from 0, 0, which was my parent function, to -1 and 0. And again, I'm going to draw my scale in here, like always. Here, you can plug in numbers and figure out your table value, or if you've started to kind of realize the pattern of how to establish your points, you can do that. If I plug in 0, it's 0 plus 1, which is 1, squared, which is 1. 1 plus 1 is 2, squared is 4, and so forth. I don't have any more room on my graph, so I'm going to stop there and add in my arrows. Again, make sure that you're curving that parabola at the vertex, not a V. Our domain stays the same. The range is now back at 0 because I haven't shifted it up or down at all. Square bracket for my defined point and positive infinity, or y is an element of the reals, but y has to be bigger than or equal to 0. Axis of symmetry goes through my vertex. That's the x-coordinate of my vertex. That is x equals -1. My vertex is now -1 and 0. My minimum, still haven't switched my upward opening, is going to be at y equals 0. My x-intercepts instead is now going to be at -1. And my y-intercept is actually also changed, even though I don't have that value out here. And so this is where that q, you can't assume that it's your constant, you can't assume it's your y-intercept. I look at my graph and my y-intercept is actually now +1. Now, if you haven't graphed your function, or you're not 100% confident in your ability, or maybe it crosses at kind of a weird spot, you plug and chug, just like we did in the previous question. So we could have done that here. Could have solved for my y value, my y-intercept. X value is always 0, plus 1 squared equals 1 squared, or just 1. And there we go. So remember, y-intercept is when x equals 0, and x-intercept is when y equals 0. E is very much the same as D. We've got a number inside the brackets inside our function, and so we are going to say that P is the value that's going to be changing my graph. And because I'm subtracting in here, I'm just looking at the value that follows that sign, so P is +4. To create my graph, that means I'm shifting it right 4, not up or down, because there's no Q value. And from here, I will create the rest of my graph. I've been consistent in my labeling thus far. Don't quit now. Always, always, always include a scale. If you don't include a scale, then you have to label specific points. That's not always the most ideal. It makes your graph really messy. So if you include a scale, the only time you need to label those points is when you are specifically asked to. From here, domain, I'm just going to do set notation this time. X is an element of the reals. Y is an element of the reals, but it has to be greater than or equal to 0. My axis of symmetry goes through my x value of my vertex. In this case, that is actually 4. So my vertex is at 4 and 0, with the minimum being at y equals 0. Again, still opening up because I haven't added that a value into the equation yet. X-intercepts, still only 1, still my vertex, because I did not shift my graph down or up. So it's just at 4. And my y-intercept, now, because it's off my graph, this is another scenario where I'd want to solve for it. So y equals 0 plus minus 4 squared equals -4 squared equals 16. So that would be my answer. So again, solve for it if you cannot see it on your graph. F changes what we're looking at again. So we no longer have that constant value inside our parent function, not inside the brackets, but instead we do have a constant out in front of the x squared. So that's our coefficient. That's the word we use to describe it. And our coefficient is a. 2 is bigger than 1, so that means that it's going to stretch our graph. 2 is also positive, which means we're still going to have our graph opening upward. This is definitely a graph that you'd probably want to consider doing a table of values for, or at least mentally figuring out what your points are going to be, because stretches and compressions aren't as intuitive as just shifting our graph up and down, left and right. So if I talk it through, 0 squared is 0, times 2 is still 0. So I can still identify that as my vertex point, 0, 0. That hasn't changed. I didn't shift it up because there's no q value. Didn't shift it down because there's no q value. Neither did it go left and right because there is no number in place of p. It is 0. Moving to the right, plug in x equals 1. 1 squared is 1 times 2 is now 2. Again, we match on both sides. 2 squared is 4 times 2 is 8. And so I'm actually already off my graph at this point. I've got points about here and here, which is kind of crazy. So that definitely is stretched out. It's also kind of looking narrower than our previous graphs. You still want to try and get that curve. Not very good, but it's going to be a little bit harder to make it a little curvy. There we go. No, not there. That looks like it's aiming at that point above the grid. My domain, still the same. Even though it's narrower, it can still go left and right to infinity. I could still plug in 1,000 for x and square it, and then multiply it by 2, and I would still get a value for y. So still, x is an element of the reals. My range also still follows the same formula because it's forever extending upward in this case, but it does have that vertex, that point where it doesn't go farther below. So that means we're going to start with y as an element of the reals, but y has to be bigger than or equal to 0. My axis of symmetry is where it crosses, where my x value is for my vertex, which is 0 because the vertex is 0, 0, and my minimum is also there. It's at y equals 0. X-intercept is 0, my y-intercept is also 0. So things from this perspective, all these characteristics, they actually look a whole heck of a lot like our parent function. So that's kind of crazy if you think about it. That a value doesn't really change anything in terms of key characteristics of your graph. You got to be careful when you're graphing it. Watch out. Always double check your a value if you're trying to write an equation. Moving on to example G. We're still dealing with a. It's still multiplying our x squared term. This time, though, it's between 0 and 1. So it is going to compress our graph. So again, start with our labeling of our scale. If we plug in values starting with the vertex, 0 squared is 0 times a half is still 0. So again, we're not seeing that our vertex has really moved. But 1 squared is a half, 1 squared is 1, times the half is a half. So now my points are not climbing nearly as fast. 2 squared is 4, but half of 4 is actually only 2. 3 squared is 9, half of 9 is 4.5 squared. Or not 4.5 squared, just 4.5. 4 squared is 16, half of that is 8, and so finally we get to a point where our points are off the grid, and we can trace our parabola shape from here. The domain has not changed. I can still plug in anything for x. My range didn't change from the previous one, or my parent one, because I haven't shifted it up or down. My axis of symmetry is still the same as the parent function because it didn't move, my vertex didn't move left or right. My minimum, because my vertex hasn't shifted again, is still going to be the same. Finally, my x and y intercepts are also still the same. So that a value really does a number on the graph in terms of what it looks like, but it actually doesn't change the characteristics. Finally, we get to h, and we get something a little bit different. It doesn't look like there's a number out in front of it, but because there's that negative sign, we treat it like there is. We treat it like a equals -1. So again, we label our scale. From here, you can plug and chug, or you can use our rules from the beginning of the lesson, after your activity, to draw your parabola that way. It reflects it over the x-axis. It makes it so that it's opening downward. But my vertex doesn't change. 0 squared is still 0, and -0 is the same as +0 because neither one really exists. It's just 0. Not positive, not negative. Right in the middle. From here, if I plug in +1 squared is +1, but that negative out in front flips my sign. Then I've got 2 squared is 4. But that negative out in front tells me it's actually supposed to be at negative 4. And so my parabola, instead of opening upward, is going to open down like this. That's going to feel a little awkward for you to draw the first time. If you need to turn your page upside down to do that, go right ahead. The domain still is the same. It is still x is an element of the reals. Or if we want to write it in interval notation, negative infinity to positive infinity. Let's fix that negative sign. Doesn't want to go away. Alternately, now my range is a little bit different because my parabola is no longer opening upward, it's opening downward, which means I have a maximum. So y has to be less than or equal to 0 instead. That also changes how I write it in interval notation because I go to negative infinity. That is the basement of this parabola, whereas the top or the peak of it is at 0. And square bracket because it is a defined point. I haven't shifted it left or right, so my axis of symmetry actually does still stay the same. It's at x equals 0. My vertex is still the same because I haven't shifted it left or right. There's no p or q values in this equation. My maximum is at y equals 0. My x-intercept is still 0. My y-intercept is still 0. So having worked through all those examples, we've seen all the different kind of variations on how we can impact our equation with one transformation at a time. And that's what those shifts and stretches are called. They're called transformations. Okay, so you've got a bunch of practice questions to do. Definitely do them for 2 reasons. Number 1, because you need to learn this. Number 2, you are going to be moving on to the second half of this lesson shortly, and that's going to involve combining these transformations. So you definitely want to be comfortable with just one of them at a time, because once we start introducing 2 of them, it gets a little bit more complicated. The third reason that you want to do this is because this actually segues really nicely into the transformations unit in grade 12. So if you're planning on continuing with pre-cal after this year, you definitely want to be a master of these transformations of quadratic functions.